Hi everyone, so here we are on Chapter 7, and Chapter 7 is on atomic structure and periodicity. There is a lot of information in Chapter 7, so we're going to break it down into smaller pieces. So just for today, we're going to just talk about light, the electromagnetic spectrum, waves, and some of that stuff, and then we'll get deeper into it. So the first thing that I want to talk about is the electromagnetic spectrum, okay? And we've talked about this before, and we're going to be talking about light and how light is a wave function. So if light is a wave function, we need to know about the three characteristics that make up a wave. So the first thing that makes up a wave is what we call the wavelength. Okay, so let me get a pointer here. All right, so wavelength, the distance between two peaks in a wave. Okay, so that is the length of the wave. And in a couple slides, I'll have some pictures of waves and I'll show you how wavelength is measured. The next thing is frequency. So frequency is the number of waves per second that pass a given point in space. Okay, so in other words, how many waves per cycle. And then of course we have speed. So light, your waves will travel at the speed of light. So this value for the speed of light, it is found on the pink sheet. So the speed of light is 3 times 10 to the 8th meters per second. All right, so now let's get into an equation. Let's take a look at this equation here. All right, so nu, this is the symbol nu. Nu is spelled N-U. It is a Greek letter. Okay, so that's nu. Nu is written like this. It looks like a V to you, but it's not a V. So this one is a straight, like diagonal line, and then the other one is going to curve into it. Okay, so that is how you write nu. Once again, it's a Greek letter. So nu represents frequency. All right, how many waves pass through in a certain amount of time. And these are your units for frequency per second. Okay, so how many waves pass per second? Per second is also what we call a hertz. Hertz is abbreviated Hz. So hertz is spelled H-E-R-T-Z. Okay, so that is what a hertz is. Now this next variable is lambda. All right, that is lambda. It's a Greek letter, and this one will represent wavelength. So in this equation, your wavelength will be in meters. And then of course we have this c here, and the speed represents the speed of light, and these are your units here for speed of light, meters per second. So you can see how all of those units have to be the same so that they can cancel out in the equation. All right, so then in this equation, and this equation is also found on your pink sheet. So this is saying nu equals c over lambda. Okay, so the frequency equals c over lambda. So to help you remember this equation, even though it's on your pink sheet, it's one of those equations that you should just always know. All right, so here's like a funny saying to help you remember it. If someone says, hey, what's new? And then you can kind of be nerdy and say c over lambda. All right, it's a really bad science joke, but it's really funny amongst chemistry and physics people. All right, so now here we are taking a look at some waves. So notice that the waves look a little different, okay? Now if you take a look at the first one, all right, so there's a lambda, and this is how we can measure wavelength from peak to peak, okay? So that's how we measure the length of a wave. Or it can be the bottom of the wave is called a trough, or we can say from trough to trough. Okay, so once again, that's how we measure the length of the wave or wavelength, peak to peak. Okay, so notice we have a red, a green, and a blue wave, and these are representing light. Okay, like a red light, a green light, and a blue light. You can see that some of them have a longer wavelength, right? The red one has longer waves, the green one is kind of in the middle, and then look at the blue one. These have really, really short waves, okay? But then look how many waves pass per cycle, okay, of unit of time. Okay, so notice the longer the waves, the less frequent the waves are. The shorter the waves, the more frequent the waves are. Okay, now just by looking at these three different waves, which one looks like it is more penetrating or like more dangerous? Well, that would be the blue one right here. Okay, your blue wave, notice it's shorter. Okay, the wavelengths are shorter and they're more frequent. Your blue waves or blue light is going to be more penetrating than something that is red. Okay, longer waves are not as penetrating or dangerous as blue waves. All right, so here is a picture of your electromagnetic spectrum. So in this electromagnetic spectrum, notice what the diagram is telling you. So this is the wavelength in meters. Okay, so this is to the -12 there, and this is to the 4th here. So the waves on this side are longer. The waves on this side, on the left here, are shorter. Okay? The visible region is this very small band. So if the waves fall in this visible region, then that is how we are able to see these colors of light. Okay? And this spectrum, we call this a continuous spectrum. Continuous spectrum meaning that all of the colors are completely blended together. All right? Now, if you remember your rainbow in the order of the color, remember it's Roy G. Biv. Okay? Red, orange, yellow, green, blue, indigo, violet. Okay? Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And then, depending on what side the wave is of your color spectrum, that will identify how dangerous or penetrating your wave is. So you can see here, things on the closer to the blue and the purple side, you've got UV, X-rays, and gamma rays. So obviously we know that these are more dangerous and penetrating than infrared, microwaves, and radio waves. Okay? So things closer to red are not as dangerous because those waves are longer. Things closer to blue and purple are higher in energy. All right? The waves are shorter, more frequent, more penetrating, and dangerous there. So you just need to be familiar with the colors of light, and how they, what kind of energy they represent. All right, so here is a picture showing two different types of light or diagrams. So this top one is representing white light. So this is white light. And that's how we're able to see rainbows and stuff. So if we have a source of white light, and you shine that source of white light, okay, here's our white light, you shine it through a prism, and then you see the rainbow of colors, all right? You see the continuous spectrum of colors. Now, instead of white light, what if we have what is called a gaseous atom? So this particular one happens to be hydrogen gas, all right? So for a gaseous atom, when we shine that through a prism, notice the rainbow of colors here. It's not continuous. This is what we call line spectra. Okay? Line spectra is unique for each gaseous atom. And that is one way that we can identify what the gas is. All right, Planck's constant. All right, so this is another equation that we are going to talk about. So there's a lot of math in this portion here. Not only a lot of math, but a lot of concepts, okay? So Planck's constant is this letter H right here, okay? This is what we call Planck's constant. Now, some people might call this Planck, or some people call it Planck. I was just taught that it's pronounced Planck. I don't know if that is just because that's how my professors pronounced it, but I always have just learned that it's called Planck, okay? This value of H equals 6.626 times 10 to the -34th joules per joule seconds. So this value, you don't have to have it memorized. It's on the pink sheet, okay? So we've seen nu before. We know nu is frequency. we know that lambda is wavelength. All right. Now we can calculate the energy. So the energy of the light or the energy of the wave, that's by using this equation. Okay. So remember, so let's take a look at it here. All right. So if energy or the change in energy equals equals h nu, right? So remember, nu, we learned that nu is equal to c over lambda, okay? So you can see how it's relating to that other equation that we just learned, all right? So this is how we can calculate the energy of the wave. This is a really good diagram showing how the different waves and the colors and how much energy is associated with those. All right, so one thing that I want to point out as you look at the energy here, these are the energy levels. All of these lines are the energy levels. Notice that the energy levels are not equally spaced, okay? As we move further and further out, notice that the energy levels get closer and closer and closer to each other, okay? So you can see here the blue light, the green light, and the red one. Notice that the blue one, once again, is associated with higher energy. The red one is associated with lower energy. All right, notice that the arrows here are pointing down. Okay, they are pointing down. So if you recall from first year chemistry, we learned like when is light emitted. Light is emitted, remember, when the electron is falling down energy levels, right? It will absorb energy to jump up to a higher energy state, but it can't stay at that high energy state forever, so eventually it's going to fall back down. And it's when it's falling down is when it will emit that photon of light, okay? And that's how we're able to see light and all the other different colors of the rainbow, all right? So once again, light is emitted when the electron is falling down energy levels. Okay, so now we're going to get into Einstein's equation. So Einstein is famous for his E equals mc squared equation. So he is associating energy and mass, okay? And then, of course, c represents the speed of light. All right, if we take a look at this equation is showing us how the energy and mass are very much related, okay? So this equation here, energy, notice it says photon here. Anytime we're using these energy equations like energy equals h nu, it is always per photon, okay? Per photon of light. And so hc over lambda, right? So we know that is one of the energy equations that we just learned a few slides previous. All right, so energy equals hc over lambda. Then if we also incorporate E equals mc squared, then we end up with this, how mass is equal to h over lambda times the speed of light. So let me show you how that is derived. Okay, so we had energy equals h nu, right? And we know that nu is equal to c over lambda. Okay? So now if we substitute in, and we now take also into consideration Einstein's equation, E equals mc squared. Okay, I'm going to substitute this in here for the energy. Okay, so it's going to look like this. So then it will be mc squared equals hc over lambda. Now, let's isolate the mass by itself. Okay, so I'm going to divide by c squared on both sides. So if I divide by c squared on both sides, then that will cancel, right? And then one of the c's will cancel. Okay, so then notice we get mass equals h over lambda times c. Okay, so that is how this equation here is derived and how it's telling you that energy and mass are very much related. All right, they have what is called a dual nature. Okay, then this is another equation that I want to go over today, and this is what we call de Broglie's equation. Okay, now it's kind of tricky because we see this V here. This one is indeed a V. Okay, it is not new, and they are hard to distinguish. You have to be very, very careful. So the V, if you look on your pink sheet for velocity, velocity has more of a pointy bottom. Whereas if you look on the pink sheet, the new symbol has more of a curved bottom. Okay, they are different. All right, so V is velocity, and that's in meters per second. The mass in this case will be in kilograms. The reason why the mass has to be in kilograms is because Planck's constant has joules in it. This right here are all the units for joules. Kilograms, meters squared per second. So that's why that has to be in kilograms to cancel out that the mass in kilograms. And then the wavelength will be in meters because we have meters here and we also have meters there in the velocity. So de Broglie's equation states that the wavelength equals h, which is Planck's constant, over mass and velocity. So we're going to take in consideration the mass of the particle and the velocity or the speed of the particle. Okay, the last thing that I want to talk about today has to deal with the spectrum for hydrogen, all right, or a gaseous atom. Remember when we saw the picture earlier, any gaseous atom, like the hydrogen one, is what we call line spectra, okay? It is line spectra. So it's not continuous. The continuous one was for a source of white light, and that's how we're able to see rainbows. You have to have a source of white light, shine through a prism, and then you're able to see that continuous blend of colors. All right, so you're able to see rainbows because what will serve as the source of white light? The sun. And then what will serve as the prism? The water droplets that are in the air. So when the sun is shining through the water droplets in the air, then that's how you're able to see rainbows. Okay, so you just need to make sure that you understand that gaseous atoms have line spectra that are unique, and that is how we can identify what the gas is, by looking at the line spectra, whereas white light has a continuous spectrum. All right, so that is all that I want to focus on today, and then we will continue the other lectures tomorrow. All right, see you later. Bye.